Hello everyone. In today's video, I'm going to discuss about BFS, that is called Breadth First Search Algorithm. We all know that BFS is an application of queues. So we discuss in detail about like how this BFS is going to work and all. So breadth first search algorithm is a fundamental graph traversal algorithm which involves visiting all the connected nodes of a graph in a level by level manner. Okay. If you take any graph or a tree, we try to access every node or try to visit every node by level. That means if you are thinking like assuming like the root is at level 0, first we visit the root. Okay, then all its children which are at level 1, we visit all the children of the root. Then in any order we can visit the children of that level 1 nodes. So in all these things, like we visit nodes in level manner, that means in breadth, like we go to the nodes in breadth wise. That's the main fundamental concept of the BFS. So you can see here like a breadth first search for a graph, something like this. So we're going to discuss about all the things like what is a breadth first search and the relation between BFS in graphs and trees and all. Then we see its implementation. We'll discuss one example. Let us we discuss about this time complexity and space complexity and applications and all. Okay, so we start this with the thing like what is breadth first search. So breadth first search is a graph traversal algorithm that explores all the vertices in the graph at current depth before moving on to the vertices at the next depth level. So it starts at a specific vertex and visits all its neighbors before moving on to the next level of neighbors. So BFSs are commonly used in algorithms for pathfinding, connected components, and shortest path problems in graphs. Okay, we know that like pathfinding means if you're just assuming like a computer network. Okay, we try to find out the path between different peers in the network, and we try to see like in different graphs and all, like we see like whether two nodes are connected or not. And in graphs for finding the shortest path, okay, we also uses BFS, right? Coming on to this relation between BFS for graphs and BFS for trees. So breadth first traversal for a graph is similar to the breadth first traversal of a tree. So both are same. The only catch here is that unlike trees, graphs may contain cycles. So we may come to the same node again. Okay, we know that like trees, we don't have any cycles. We call it as acyclic graphs. But in graphs, there can be cycles. Okay, so when you are trying to visit every nodes and you come again to the same node, so we can say that there has been a cycle in that graph. So to avoid processing a node more than once, we divide the vertices into two categories. So we divide the vertices into visited and a not visited category. We can use a boolean kind of an array kind of a thing to maintain these visited nodes or vertices. And for simplicity, is assume that all vertices are reachable from the starting vertex. Okay, so BFS uses a queue data structure for traversal. We know that BFS is the one, it's an application of the queues. So breadth first search for a graph algorithm is like this. Okay, the first step we do in BFS is we initialize. So we initialize the queue. That means we enqueue the starting node into the queue and mark it as a visited. That means the root of the tree, or if it is a graph, we start with any node, we say that is a starting point. We just enqueue that node into the queue, right? Then second step is called the exploration. Okay, what do you mean by exploration is like if the queue is not empty, what we do is we dequeue the node from the queue and visit it. That means we try to print that node on the screen when you're implementing that. Okay, and we just put that node as marked as visited, or we just uh, insert that node into a array kind of a thing. We call it as a visited node. Okay, then what we do is like we will visit all unvisited neighbors of dequeued nodes. Okay, that means like whatever the nodes that are connected to the first node, which is we set it as a visited, will enqueue all its adjacent nodes into the queue. in a any order, right? So that means, so for each unvisited neighbor of the dequeued node, what we do is we enqueue the neighbors into the queue and mark that neighbor as visited. Okay, we repeat this step 2 until there are no nodes that are unvisited. Okay, so the termination point will be, we repeat the step 2 until the queue is empty. That means we do this or keep on do this until my queue becomes empty. So these are like an algorithm or kind of a methodology that we use in BFS. Okay, so we try to explain this concept with a kind of a diagram and all. Okay, so how does this BFS algorithm works and all, right? So we'll discuss like how does the BFS algorithm work. So starting from the root, all the nodes of a particular level are visited first. Then the nodes of the next level are traversed till all the nodes are visited. To do this, a queue is used. All the adjacent unvisited nodes of the current level are pushed onto the queue, and the nodes of the current level are marked visited and popped from the queue. Okay, so we just illustrate this with the kind of diagrammatic things and all. Okay, so let us understand the working of the algorithm with the help of a following example. So take this graph. Okay, initially the queues on the visited arrays are empty. Okay, you can see that this is a graph. Okay, there are five vertices which are marked with numbers 0, 1, 2, 3, 4. You can see that the adjacent nodes for the 0 is 1 and 2, and the adjacent nodes for 1 are 0, 2, and 3, and the adjacent nodes for 2 are 0, 1, and 4, and the adjacent nodes for 3 is 1 and 4, and adjacent nodes, or you call them as the neighbors for the node 4 or 2 and 3. Okay, so if there is an edge between two vertices, we can say like they are connected, or we can say they are the neighbors, right? So you can see that we have taken two queues. Okay, so one is called we named it as a queue, and another one we call it as a visited kind of a thing. So we know that queue will have a front and rear. Okay, so at the front, the DQ, that is removing the elements, will take place. At rear, okay, we insert the elements into the queue. Okay, so this is the initial diagram that we have actually using for this explanation and all. Okay, so the first thing is like we push node 0 into the queue and mark it as a visited. You can see that in the diagram I turn this color into red. Okay, so the first node that we are visiting is vertices 0, so we just enqueued that 0 into the queue. Okay, so at the same time, since we have actually visited 0, so we are putting that 0 into the visited array. So you can see that the second array, or you call it as a queue, you can see that that is actually visited. Okay, so in the next step, what we do is, what are the adjacent nodes here for the vertices 0? So the adjacent nodes for the vertices 0 is like 1 and 2, right? So in the next step, what we do is like we enqueue, that means we insert both the neighbors of vertex 0, that is 1 and 2, onto the queue. So in this next figure, you can see that, okay, 1 and 2 are inserted into the queue. And what we do is like we just dequeue the vertices 0, because we already visited that node. We dequeue that 0 from the queue. So the next elements that are in the queue are the neighbors of the vertices 0, that are 1 and 2. So already 0 is, we said, like visited. Now we have actually inserted or enqueued vertices 1 and 2 into the queue. So we put this 0, 1, and 2 as visited in the upper array or upper queue, right? You can see that. So the next one to be dequeued from the queue is like 1 is at the front. So we dequeue the 1, okay? So and we push, or we, what do we say? We enqueue the elements which are the neighbors of what is 1. So the vertex 1 are having three neighbors like 0, 2, and 3, but already 0 and 2 are in the visited list. So the unvisited neighbor of vertex 1 is the 3. So the next element enqueued into the queue is 3. So in the next figure, you can see that 1 is removed from the queue, that is dequeued from the queue, and 3 is inserted into the queue, right? So this will be again the step 2 is repeated, that what is the node in the front, that is the vertex 2. So the vertex 2 we keep it as a visited, and what are its unvisited neighbors? You can see that 2 is having a three neighbors, that is vertex 0, 1, and 4. already 0 and 1 are in the visited list. So we enqueue the element 4 into the queue, and we just remove the element 2 from the queue. So in the next step, you can see that so 3 and 4 are in the queue, and 0, 1, 2, 3, 4 already in the visited list. So then we say like what are the unvisited neighbors of node 3, because the 3 is having a neighbors 1 and 4, both are already visited. So we just remove the 3. Okay, then we'll have a 4 in the queue, and we see the neighbors of 4, and the neighbors of the 4 are 2 and 3, which are already visited. So we also remove the 4, and we don't have any unvisited nodes. You can see that in the figure every node is turned into a red color. Okay, so all the nodes, that is 0, 1, 2, 3, 4, all are visited. Okay, so we can say that the BFS has completed the concept, and we just stop the concept now. So we can implement this breadth first search algorithms for graphs using adjacency list. Okay, so we can write a function for a breadth first search algorithm, and we can use this map as an adjacent list to mark and everything, right? So this is the code for the implementation of BFS. Okay, so this is so we have written the code in Python actually, right? So you can see here like there is a function called BFS. So we define the BFS function, and we are sending a uh, three parameter values. One is the adjacent list, and another one is the starting node, and we are sending another parameter as visited. Okay, so we create a queue for BFS by using a DQ. So there is an already predefined method called DQ. So we are creating that DQ to create a queue, which is stored into a variable called queue. So queue is nothing but an empty queue has been created. So there is a list which is called visited. Okay, so that visited list is having a index value as a start node. Okay, so start node, and we make that visited list as a true. So the first node that is actually into the visited, that is the root node, will be termed as a true value, right? Then what we do is like we just append that start node onto the into the queue. Okay, so you know that like so by putting a value 0 here, you can see in the figure like first time the value 0 is actually put in the visited node, and as well as they are appended into the queue. So that step is actually written here, right? So that's the reason why actually appending that start node to the queue, right? So if there are any queue elements left in the queue, like if there is an element in the queue, so what we do is like we just remove the element by using a built-in method called pop left and put it into the current node, and we just print that current node on the screen. Like we want to see like BFS how the order of visiting the nodes, so we want to display it on the screen. So for that purpose we just print that node, right? So the current node will be printed. So this will repeat until all the adjacent vertices of the current node are pushed onto the queue, and everything will be visited, and all the visited nodes are actually displayed on the screen, right? So that's the thing, right? So what we do is like we need to identify the neighbors, and if there are any neighbors, what we do is like for neighbor in adjacent list. So what we do is like adjacent list of current node. If that node is not visited, what we do is we take that neighbor node and put it into the visited and make it as a true, and we try to append that neighbor into the queue. Okay, so that's the thing. So here what happens is that step number 2, that is enqueuing all unvisited nodes into the queue and making them as visited until every node in the graph or tree termed as a visited and all. So that will happen in this particular loop. So this loop will iterated until all the vertices in the graph or tree are marked as visited and all. Okay, there is another method called add edge. So we thought like, so we want to represent our graph or tree by using adjacent list. So what we do is like we add the edge. So we take this adjacent list and we take two values like u and v. So what we do is like for every adjacent list for the index value u, so we append that v, that is the vertex. So here is the main method, like main So the definition main. So what is that is like in this particular example, I want to take vertices, 5 vertices in my graph, right? So what we write is like we try to create a list that is called adjacent list. So then empty list is created for the first time, and for every vertices, that is the 5 vertices, this can be adjacent list will be created. So the edges for this thing is like add edge, like we have already defined the method called add edge. So for that we are passing these things like adjacent list, that is the empty list that we created first, then we are trying to give that u and v values. So if you are giving 0 and 1, that means u is 0 and v as 1. So that means there is an edge between vertex 1, 0 and 1. Similarly, in the next time again we are calling that method add edge or the function add edge. So we are sending again adjacent list and we are sending like 0 comma 2. That means there is an edge from vertex 0 to 2. Similarly, there is an edge from 1 to 3, 1 to 4, and 2 to 4. So these are uh, 5 vertices that we are sending to that thing, right? So in the beginning, what we do is like for all the vertices, that is the 5 vertices that initially they are actually initialized to the false value. You can see that visited is equals to false multiplied with the vertices. So every vertices will be initially stored as a false. Then we call this main method and your program will get executed. Okay. So the output will be like the breadth first traversal from the vertex 0 or 0, 1, 2, 3, 4. So this is the output that we get from the above code. Okay. So here you can see that we can estimate the time complexity as well as the space complexity, right? So the time complexity for this program or algorithm is the order of v plus e. That means we are visiting every vertex in the tree and as well as the vertex in the graph and as well as every edge. So we can say the time complex is order of the sum of vertices plus edges, where v is number of the nodes and e is number of edges. Similarly, the auxiliary space is like we have to store every vertex in the graph into the memory. So the total space occupied by your graph is like the order of v, that is the number of vertices. So the complex analysis of the breadth first search is something like this. Time complexity of BFS algorithm is like order of B plus. We already said that BFS explores all the vertices and edges in the graph. So in the worst case, it visits every vertex and edge once. Therefore, the time complexity of BFS is order of B plus U, where V and E are the number of vertices and edges in the graph. And the space complexity is BFS uses Q to keep track of the vertices that needs to be visited. In the worst case, the Q can contain all the vertices in the graph. Therefore, the space complexity of BFS is order of V. That's the thing. Like so, the finally we try to see like what are the different applications of BFS and graphs. Okay, so BFS breadth first search has a various applications in graph theory and computer science. So the first applications we use this BFS is for the finding the shortest path finding. So BFS can be used to find the shortest path between two nodes in an unweighted graph by keeping track of the parent of each node during the traversal. The shortest path can be reconstructed. And there is another application called cycle detection. Okay, so BFS can be used to detect cycles in the graph. That means how we do is like if a node is visited twice during the traversal, that indicates that there is a presence of a cycle. Similarly, there is a another application is like to find whether the two components are connected or not. Like in BFS can be used to identify connected components in the graph. That means each connected component is a set of nodes that can be reached from each other. If one node is reached from another node, we can say they both are connected. Similarly, we can use it for another application called topological sorting. So BFS can be used to perform topological sorting on directed acyclic graph. We call it as a DAG, okay, DAG. So topological sorting arranges the nodes in the linear order such that for every edge UV, it appears U before V in the order. And another application is level order traversal of binary search. We all know that binary in the binary trees. So what we do is like BFS or breadth first search can be used to perform level order traversal of a binary design. Okay, you know that means every nodes in a particular level will be visited. Then only we move on to the next level. And another application is called the network routing. Okay, network routing is like BFS can be used to find the shortest path between two nodes in a network, making it useful for routing packets in a network protocols. You know that in computer networks, the packets will be transferred from one node to another node. So we try, when we're sending packets from one sender to a receiver, we try to find out the shortest path between the two nodes. So in that case also we can use. Okay, so this is the total concept of BFS, breadth first search algorithm. Okay. I hope this video is useful for you. Thank you so much for watching this video. Thank you guys.